As Shraddha has said, my topic is decarbonization of cooling through passive design and low energy cooling technologies. So to begin with, some statistics. We all know that cooling has gradually increased, but here are some global statistics which say that the amount of cooling appliances globally is expected to increase from 3.6 billion to 9.5 billion in 2050, and cooling energy for cooling is expected to almost double to 7,500 terawatts hour into 2050. And most of the carbon dioxide emission, that is almost 11.8% of the world's direct carbon dioxide emissions, will be on account of cooling. And when we say this, the cooling accounts not just the cooling for buildings, but also refrigerator vans, mobile freezers. We use cooling in so many places, including the medical systems where 24 by 7 cooling is required. So given this as a background, and just to give you a statistics about the world, in Saudi Arabia, 70%, more than 70% electricity is consumed for air conditioning and cooling. I was there in Dubai recently, and I found that most buildings do not shut their air conditionings at all throughout. So it's a massive guzzler, especially in places which are extremely hot. So if you look at the Indian scenario, the situation is rather similar. Only thing is that here, even in the residential sector, the cooling has increased by leaps and bounds, and we're expecting a huge increase, especially in the residential sector, which is why some policies were introduced. So, of course, commercial spaces, 60% of the commercial space in India is expected to be air conditioned, and we're expecting a nationwide increase in the number of air conditioning systems, almost 2 to 3 times by 2027 from the business as usual scenario. And as you can see, space cooling and fans, they constitute the largest component of the electricity, that is 33 to 65% of the electricity consumption in multi-story buildings, which is the largest category of residential buildings coming up. So India as a developing country has increased its carbon footprint. It's third in the world in terms of its carbon emissions, and the majority of this will be on account of cooling right now and also going in the future. And the question is how we can change this. So my outlook, since I come from the architectural fraternity, is how we can make buildings design better. Of course, there are three parts. One is the passive design, which is how we can, do the orientation of the building right, the shading design, the building envelope materials, that is their U value, thermal transmittance, and by using various passive design strategies. And of course, active design has been there for a while, solar, rooftop, BIPV, and so on. And then there are these complex systems, that is the thermal heat exchange systems, which I'm sure some of the other speakers will talk about. So when we talk about passive design, and I really briefly explain the building envelope. So, what is the material of the roof, and especially this aspect called U value, thermal transmittance, and same for the wall as well as for the glazing, it matters a lot. And when it comes to the glazing, the orientation of the glazing and the solar heat gain coefficient, these are aspects which are very important. So once a designer knows about these things, knows how the building physics works, then a big battle about cooling is going to be won, because the cooling load will definitely come down. So passive design strategies are very simple. We have the shading devices. We have Rice's Soliel introduced by Le Corbusier in Chandigarh. Then we have the solar chimney, which has been used in this example in a Terry building in Gurgaon. And then we have, courtyards, which have been essentially part of Indian architecture. And even things like the Trom wall. These are all passive design strategies which can be applied. And we see this in some of the new buildings beautifully applied. Like, for example, in the bottom, we see the Z building, which uses solar chimney. The Trom wall system, this is used in a building in Lucknow, a pharmaceutical. Then we have the wind towers, we have the Jalis, and where this is the Norman Foster's building in Abu Dhabi, and so on. So all of these are using the traditional principles, using building physics, and making the buildings consume low at by using passive design strategies. So there is also going further, when especially in the modern era and when we have high-rise buildings and we have the huge issues related to urban areas where there is noise, dust, and natural ventilation has become practically impossible, then we look at the principles of passive house design, which means we have super insulated buildings which are devoid of any thermal bridges, where the heat energy flows from one building element to the other, then having a compact form, having an airtight building envelope. So, optimal use of passive solar gain, so making the most of the sun's energy wherever it is required and whichever part of the year it is required, and having a completely mechanical ventilation system with heat recovery, which means that you get good fresh air, clean air at the same time, while you do not compromise on the indoor environment quality. And the next step, of course, active design. I won't go much into detail, except that there are lots of buildings today where we have studied that, by a combination of wind as well as solar rooftop, especially housing societies have been able to deal with a lot of their loads and bring down, like, for example, in some cases, air conditioning systems or lighting systems and so on. So these are all methods. And then we have some very good examples like the CARB net zero energy building, which is a combination of passive design as well as the best of the active systems. And it's like a model building which consumes very little energy or very little to low energy. And of course, there are ideas like the district level cooling, which is a kind of scaling down, but at the same time scaling up. And the advantages of this is that cooling can be achieved, but at the same time, you can use the heat energy for your other purposes. So it's a combination of things, and at the same time, energy is efficiently utilized, but at a district level, at a larger scale. So just like any other system, it is piped and brought into the houses and much more efficient and controlled. And then we have new technologies such as the phase change material, which can be used in the building envelope, and which helps in to modulate the and keep the internal temperature in balance by changing according to the external stimuli. There are two examples which I'll very quickly share. One is a college building which was located on the 6th, 7th, 8th story, which we entirely renovated for the purpose that it was extremely hot. There was a big issue of thermal comfort. So we used low energy cooling technologies. There were 2, 3 things. Of course, we did the spatial retrofit and the structural retrofit of the building, like opening up the windows and removing the false ceilings and all. But a few things that we did was the changes in the roof to bring in more light, to have a thermal barrier, which is a low emissivity material, and we use turbo ventilators, so to create stack effect and all. And much of this was also done using simulations. So we did this simulations. So these are the things that were done. And internally, we did a lot also for the noise control, like the dry walls, noise as well as thermal control. So these are a few of the things we did, and the results were really remarkable in terms of the outcome, because this was also kind of study project where we were studying how the outcomes were. So just to show you that, between before and after, when we compared the roof bottom temperatures, they were almost 12.5, 12.6 degrees, change in the roof bottom temperature. And also we did PMV, PPD studies to see how people feel, how thermally comfortable. So this was all completely low energy systems. There was no high tech, no air conditioning involved, and yet we were able to bring down and bring thermal comfort. The second case study is a building in Nasik. This is an office building, and this is a study, like we did a research, kind of a short research on this building. But this was the one for which we got the Best Paper Award in Hong Kong at the CLIA International Conference. So this is called a thermo drain system, where there is a structural cooling, the pipes are laid inside on top of the slab, and you have the cooling done through the water, which is, from the underground tank. And of course, it was there were sensors to check the temperature of the water and so on. But what we found was that this is a system. So, during the time of construction and post-construction, we had high albedo paint and all that. But this is how the system worked. So there was a balancing tank, underground tank below the building, and there was a radiator and night cooling system. So by which, and what was surprising is that when we use a tropical summer index, which is one of the best indices to measure thermal comfort for India, we found that the thermal comfort in this building was within the acceptable range. It was 27.4, and that is the closest to the optimum value of 27.5 that was expected. So this was a very remarkable output that we found. So just a little bit about what are the regulations and policies related to cooling. We have the Energy Conservation Building Codes right since 2007, and the latest version of the Commercial Code, which is ECBC 2021, as well as for the Residential Code, Eco Nivas Samhita, has been released. And in many of the states, it has also been made mandatory, not all states. And then we have the India Cooling Action Plan, which gives broad ideas of what needs to be done in the cooling sector for best results. We also have the India's overall nearly zero energy or net Z policies for buildings. And example of this is the Paryavaran Bhavan in New Delhi, a very good energy positive building, which has a huge number of solar PV panels on the rooftop. And one of the important things about this building is the passive design that they have achieved by means of daylighting. Daylighting has been well done. And for a building which works during the day, this is essentially a big, saving. So I would stop my presentation here so that we can have more discussion later. Thank you.
Thank you, madam, for your valuable insights.